So first of all, I want to describe the instrumentation here. So here we have, in this particular setup, we have two different cameras at the end. We have the K3 and the regular camera with the scintillator. So Inoke has discussed everything about the K3, their detection. So we have pretty much two different detectors at the end. So the K3 is sitting before the scintillator-based camera. Both detectors can be operated in FTEM or EELS mode. You just have to click on FTEM if you want to do FTEM, or you want to click on EELS. If you want to use the K3, you just select the K3. If you want to use the other detector, you select the other detector. So we're going to be using both detectors here. For those of you who are not very familiar with GMS3, pretty much we have this is divided in applications, and we are going to do pretty much all STEM-based technique. And then at the end, if we have time, we'll do some TM imaging. Okay, so since we're doing STEM spectrum imaging, I'm going to click here. Okay, so we have everything we need for spectrum imaging. Okay, so we can actually control the microscope through the Gatan interface. Okay, so let's start scanning the image. Open the blank. Okay, we want to use the K3. So we're going to insert the K3, right click, insert the K3. So the software is inserting the K3. The K3 is, like I mentioned before, the K3 is sitting before the scintillator-based detector, okay? So now it's inserted, and you operate the K3 just like any other detector at the end of the GIF. So the user interface is exactly the same. So if you click here, you have the dispersion available with the K3. So you have two aperture, small aperture, large aperture, and a different set of dispersion. So we started with the dispersion 0.9 because 0.9 gives a 3000 EV energy range. So this is actually a good test to see the good point spread function of the detector. So we'll do some mapping. Well, we map pretty much everything from carbon all the way to ruthenium. Okay, so the sample is multi-stack. Right now we rotated, but you could you want to go across the interface. So right-click, draw like a line. For those of you who are not very familiar with this functionality, which is typical of GMS3, and now it's a line because we're going across the interface. Let's go up in resolution. Let's focus on the image. We use focus loop. You can change the area. With the arrow key on your keyboard, you can change the number of pixels inside, right and left, or you can increase the dwell time, up and down. And then you can focus to get the good image. So right now with the microscope, we have about 200, 250 picoamp of current. Okay. All right. So now, first of all, quick things that we want to do. I'm still scanning, so that's good. So we start the K3. So right now we have a K3. The K3 can be operated in single mode and in dual EELS mode. So we also have dual EELS available with the K3. We didn't have dual EELS with the K2. Now the energy. So there's one thing that you have to remember. That's the only important thing with K2 or K3. So if you type 0, automatically the software is changing the lifetime. The lifetime is the electrostatic shutter. The electrostatic shutter is basically located above the prism. So you can control the amount of intensity. Now the zero loss peak is very intense. So you need to activate the electrostatic shutter to attenuate the beam. So now I'm clicking, so you have a nice zero loss peak. The only thing that you have to do is just making sure that it's centered. So you have a 2D view of the EELS spectrum, you have a zero loss peak. So first thing we want to do something very easy. We have everything. We have if you type like 400 here from like nitrogen. So the software is now starting around 200 EV, so which is fine for carbon and everything else. So you see that you're going from 200 EV all the way to 3,300 EV. So we have a very large energy range. So at this point, we need more intensity. So you just type 100. So now you have electrostatic shutter fully open. Okay, so you have quite a lot of intensity now. It's not saturating. It's just the color. The software thinks that you're saturating, but you're not saturating. And you could tell by the shape of the spectrum that you're not saturating. So preview. Okay. So preview here. So let's. So we have a lot of elements here. So let's do like a 2D array. And let's look at this region here. So the way you operate this detector is essentially the same as any other detector. So let's use a long exposure time, maybe 5 milliseconds. So we'll take a minute to complete the whole area. You can see we already have a little bit of titanium. And you could do live mapping if you want, but let's do without live mapping first. Say capture. So the software is now collecting all the elements here. It's going pretty fast, 200 spectra per second. So this is actually it's not very fast acquisition, but it's just to show you a little bit, the quality of the data. And then we can make the detector go much faster. So the K3 is capable to run 3,000 spectra per second. Yeah, so basically, this is a spectrum image. Right click, we're looking at an interface, so we can average spectral on the interface. And this is the quality that you get. So you see very nice titanium nitride. It's beautiful titanium nitride. This is this little peak that we can see. This is the titanium L1. So we even see minor edges. But let's try to understand what's happening when we go along the interface here. So we have ruthenium there. So you see the ruthenium nicely. And you actually see even the ruthenium. This is a ruthenium M23. So this is a minor edge of the ruthenium, and it's visible. What about high energy? So we even see the ruthenium nicely, the ruthenium at high energy here. And if you keep going like this, you actually see even there's a little bit of strontium there. So you see pretty much everything. What about the oxygen here? So let's check the oxygen. You see even the titanium is now changing, going from here, look at this. From here, this titanium nitride. You can see the pi star peak of nitrogen splitting here. And you can see the nitrogen nicely. But what happens when we get to the STO? So you clearly now see the peak is split now. You have the 4 peaks. So we need a little bit better energy resolution, but we're using 0.9 eV dispersion, and we are getting a field of view of 3,000 eV. We actually see a little bit of nitrogen, a little bit of copper, probably copper 2+ here at the interface. Okay, so you can appreciate the very high quality of the spectra, very good energy resolution. So let's try to do some mapping now. So you go to elemental quantification. You could use the periodic table, or you could open a preset table. So I have this element of ruthenium, carbon, nitrogen, titanium, oxygen, silicon, and strontium. And we can map them, and you can display in the same workspace. So let's see what the software does. Yeah, you're getting a very good maps here. You can separate the ruthenium nicely. You can see the ruthenium. You can separate the strontium. This is complicated because there's a very minimum amount of strontium, and it's overlapping with the silicon as well. And you can map all the other elements easily. You can see the carbon as well. Titanium. You see the titanium on the STO there. So you see pretty much every element. You could do some color mixing here. So let's put the silicon. Let's put the titanium, ruthenium, oxygen, nitrogen. Yeah. So these elements should be fine. Yeah. So you see like quite a lot of color. Maybe we should change the color of ruthenium. Let's make a red. Yeah. So you see pretty much all the elements here. This was done in a minute. Interesting thing, can we do this live? Of course. So blank the beam. Let's do this other area. So this point, you want to select the live map. And you can go to the periodic table to set all the elements, or you can just go on to your preset list and select the elements that you want to map. It's very convenient if you basically work with the same number of elements. So okay, and at this point we can capture again. So let's see what the software does. Same exposure time as before. So the software is already generating maps live. There's no any loss in speed. Yeah, you see like maps again, very good. Actually, I want to show you the improvement of the quality. So this is one spectrum. This is one spectrum with 5 milliseconds. You can already see the fine structure of titanium. But look how good it is, how good improves, how well improves as soon as you sum frames. This is now the level of a simulation, and you can actually see that even the titanium. This is the titanium L1. So this is actually, pretty good, pretty compelling. So yeah, and you can map again using the elemental quantification. Okay, so next experiment, again, you can look at the ruthenium. Ruthenium looks really good. This is no longer titanium. This is actually ruthenium M23. So, and it looks really good. The quality of this data is very good. You can actually see, if you can see nicely the split of about 2 eV in the pi star peak of carbon, which is an indication of titanium nitride. So everything looks really good. Can we run faster? What about we run these? Let's decrease the exposure time to the maximum. So now we're running the system at top speed, and we want to match the same exposure time of like a minute. So I'm gonna sum frames. So essentially, we're gonna do this multi-frame acquisition. Okay, I'm gonna do like 14 frames. Okay, and you can apply drift correction. So you can put a drift correction, and you can tell the software to do the correction every frame, and you just place somewhere. Basically, the total exposure time is similar to what we had before. Okay, but I'm only summing frames. Ready to go? Let's get a good quality image because we're doing drift correction every frame. You could go see the drift correction here just to make sure. Yeah, it says every frame. And we're doing live mapping as well. And now we're good to go. Click OK. So the software is doing, making sure everything is corrected for drift. And now it's starting the acquisition. So you see like very, very fast. This is running the K3 at top speed, the 3000 spectra per second, a live mapping, and we're still able to map all the elements, including the strontium. This is pretty remarkable. And we are doing drift correction at every frame. You see the maps are getting better and better, but now the camera is actually faster than the software, because the software is doing computation pixel by pixel. So because the camera is now very fast, the software sometimes is like skipping pixel to keep up with the software. So the acquisition is done now. So the software is now recomputing all the maps, because the maps were acquired on the single spectrum, and now they're acquired on SAML spectrum. So you see now the quality is much better, but of the maps. It's similar to what we had before. What about the spectra? So again, let's click. Actually, let me clean this one for ease of use. The quality is still the same as before. We didn't see any drop in quality. What about the high energy edges? We can still see the ruthenium very nicely, despite that we use a very short exposure time. This is 340 microseconds. This is a very short exposure time, and you see nicely the ruthenium L3 and L2. And you can definitely see the strontium as well. This is really remarkable. You see pretty much everything in here. And you see now different fine structure of titanium. So it looks great. Okay. I think now we are ready to switch the detector. So let's try to compare these with the other detector. Exactly the same area. So I'm not going to change the area. So I'm going to take the detector out. And I'm going to insert the other detector. So the software is retracting the K3. So now we have the regular detector. So the software is going to change, it's going to load the settings for the scintillator-based detector. Okay, so now we have the other detector. So we want to compare 3000 EV with 3000 EV. So we need to use, we need to load the regular detector is 2000 pixel by 2000 pixel detector. So if you want to have 3000 EV, you need dispersion 1.5. So we didn't have dispersion 1.5 with the Quantum because the Continuum has a different slit mechanism. So we can actually open up the slit more. We can focus the spectrum in the center. We can open up the slit more, wider. And as a result, we get a larger portion of the spectrum. Yeah, so we have dispersion 1.5. Let's do the same thing we did before. Let's make sure the zero loss peak is 0. Let's go short exposure time. So for those of you who are using the Quantum, the Continuum, you might be familiar with these different setup, HS plus, HS, and HQ. So basically, the HQ would give you the highest quality, and this is completely unbinned. So basically, it's a 64 pixel by 2048 pixel. So the HS is actually binned on the vertical axis. So essentially, just to give you like speed, but you actually benefit of speed in this case only if you go really fast. I mean, over 3000 spectra per second. And the HS plus is what gives you the ultimate speed. But because we're going to be running these 3000 spectra per second, so I want to get the best quality. Okay, first experiment. Let's make sure that zero loss peak is centered. Blank the beam. We had a little bit of drift, so let's move our area. Let's check the zero loss peak. So it'll be off. You can even stop the acquisition, put the beam at the center here, and tell the software to align. And I mean, if you want to have a, focused, you can go on the autofocus. So the software will focus the zero loss peak automatically. Something important to remember is the zero loss peak in the case of a scintillator-based detector has a Gaussian shape. Okay, so in general, if you already see 3 pixels, that is probably the best energy resolution that you could get. Okay, this is because this is a scintillator-based detector, and the zero loss peak has a a Gaussian shape. Okay. So we focused, changed the energy. So now we're going from 500 all the way to 3,300, same as before. So we want to increase the exposure time to, I guess, 0.3. So you just type here. So this is actually similar as before. So let's put the beam, and yeah, we already see something despite the short exposure time. So this is using the regular detector. Okay. So let's refresh the image. It's got a good image here. And I'm going to be using exactly the same setup as before. So let's adjust the area, drift correction, and then we are about to start. And we'll do like the live mapping as well. So we're using 14 passes, same as before. Exactly, this is the same acquisition as before, captured here. So the software is still able to map the ruthenium. This is the ruthenium M at 200 eV to do the oxygen. It's failing on a little bit the silicon, but it's failing on the strontium. This mapper not as good as before, but nonetheless, the software is still able to create some maps. Remember, we are using the regular detector. Yeah, actually, the software did. The regular Continuum did a good job. We have good maps. I mean, the mapper is not as good as what we had before. So this is with the K3 with the same conditions. But they're still good maps. So let's try to look at the spectra now. Right click. So let me clean the spectrum. So the spectra looks pretty good. What happens at high energy? Yeah, too much noise here. You barely see the silicon, but too much noise. What about the ruthenium at high energy? You don't see the ruthenium very well at high energy. What about the strontium? You basically see something like that with the strontium. Let's try to compare. This is actually with the regular detector. So I'm going to call it like regular CMOS. Let's try to compare it with the K3. So I'm going to duplicate and move this workspace here. Okay. So sorry. So this is going to be and it's the same number of pixels, exactly the same number of pixels. So let me clean. Okay, and then I'm going to overlap. Okay, so this is actually roughly from the same area. Okay, let's try to compare regular CMOS here with the K3. Let's try to understand. Let's try to understand the advantages of the K3. So this is a K3 spectrum here. And this is a regular detector. Still looks pretty good. What about high energy? That's what you get at high energy because the signal is low. It still looks pretty good on the K3. Okay. What about What about we look at the ruthenium now? Unfortunately, they're not exactly in the same position. So I need to create another one. The sample drifted a little bit. Okay. All right, so this is extracted from the ruthenium. This is the regular detector, and this is the K3. So you see a massive improvement. So one question is, why the K3 looks much better than the regular detector? And the reason is because, like Inoke explained in his showed you like during his presentation, the K3 doesn't have, because we're counting each single electron. We're not limited by instrumental noise. We're only limited by shot noise, essentially by electrons. So if you sum electrons, you're good. You know, overall you get to the same number of total number of electrons. But in the case of the regular detector, the scintillator-based detector, if your signal is too low, and it's too low because we are using a very short exposure time, you are dominated by the instrumental sources of noise, which are not present in the case of the K3. Okay, very good. So you also see the difference in energy resolution in the titanium. You can tell this is a titanium 4+. This is not a titanium 4+. You can tell. Okay, so now let's try another experiment again with the scintillator-based detector. But now we go to one frame only, and we do 5 milliseconds. Let's see what happens. So it's about 1 minute. It was 1 minute before and 1 minute now. So we don't need drift correction now. So overall, we're spending the same amount of time, but each spectrum is going to have now much more intensity. So now we are trying to increase the amount of intensity per spectrum, because we want to make sure that we are not dominated by the instrumental noise. Okay, so you see now the maps are much better because now each spectrum has a lot more intensity. Okay, so so you're dominating now the instrumental sources of noise. So let's check the spectrum now. Oh, let's recompute all the maps. Okay, so the maps look much better now. So let's check now the spectrum. Clean the spectrum. Let's look at the ruthenium again. See, now you see a little bit better ruthenium. It's not as good as the K3, but it's becoming a little bit better. What about the titanium? You start to see the titanium. This was done with 5 milliseconds. Still not as good as the K3. This is basically the K3. And you see the ruthenium very nicely with the K3. So we could go to the K3 here. So you see the ruthenium very, very nicely. This was done with 0.3 millisecond exposure time. But actually, this is a very nice experiment because it shows you the noise that you have in the scintillator-based detector. And it shows you, this is a very good experiment that shows you the importance of counting, because when you count, you're not limited by instrumental sources of noise. So it doesn't matter which exposure time you use. If you sum frames, you will still get to the fixed number of electrons. But in the case of a regular detector, it really matters. So now you can see something here, and you couldn't see the strontium before. Look at this, same number of electrons. That's the strontium before, and again, same number of electrons. And this is the strontium now, because now we are dominating the instrumental sources of noise. Okay, so now we've done this experiment. So you see now the advantages of the K3. So let's look at different experiments. Let's do now some dual EELS with a different dispersion. So we want to do some chemical analysis. You don't have enough energy resolution. Look at this. So you can't tell much. You can tell the difference between these two different type of titanium. So that's not good. So you need a little bit better energy resolution. So we got to dispersion 0.3. Dispersion 0.3, I'm actually now having a much shorter energy range. So if you look at the spectrum now, you can go dual EELS. So you have 0 exposure time here. You can use a short exposure time. And perhaps you can start this from, I don't know, maybe from 250. So you also get a little bit of the ruthenium, okay? So I want to use 5 milliseconds, okay? Same as before. we can focus. So you can tell the software, you see there is it's dark here. So you can tell the software to focus, autofocus. Okay, so let's try to focus this a little bit better. So user tune. So this is something new that we introduced with the Continuum. So it looks like, when you do the monochromation, so it helps you to focus the spectrum manually. So basically go to here, user tune. Automatically you see the red one here. So that helps you. You could play with, with the focus. We can make it a little bit thinner. So you see pretty good energy resolution already. Something like that. You see maybe there's a little bit of S6 because that's the shape of the boomerang shape. Yeah, that's good. Maybe some FY. Yeah, that's the best. You can see that it's already like 3 pixel. So, 0.9 EV energy resolution. That's the best that we could probably do with this version 0.3. Let's make sure to have these right in the center. And you can also use zero loss peak lock to make sure that this stays in the same position. So basically, the software is now centering the zero loss peak, and at the same time is doing the correction on the core loss. Okay, very good. We have everything set up. So we're using 5 millisecond exposure time, 1 minute, very fast acquisition, capture again. Oh, of course, we don't want to do live mapping because we have elements outside the field of view. This is only for chemical analysis. So the acquisition started, 5 millisecond exposure time. And we'll do something similar for the other detector. So we don't have now, because we're using zero loss peak lock, we don't have to do any correction later. So everything is nicely corrected for energy drift. That's quite important if you want to study some fine structure or some changes. All right, very good. So this is regular detector again. Right click here. Well, actually, let me show you one thing. So when you do dual EELS, because you get a lot of things, you can just right click on the simultaneous ADF image and open a spectrum there. So if you do that, you don't have to worry about it's actually displaying in a nicer way. Yeah, this spectrum looks pretty good. You see like a very good quality, good energy resolution. Still, you're not able to resolve nicely the like the strontium, but it looks the same as before, what we did with the K3 before. Okay, and you can see the chromium nicely. So it looks pretty good. Let's try to do that now with the K3. All right, I loaded the K3. So now we have an energy range of 600 eV. So we want to do the same with the K3. So we choose a dispersion of 0.18, although we could do with 0.45, but let's do 0.18 so that we have the same one. Okay. And let's switch to dual EELS. So dual EELS K3, same as before. Okay. So you have essentially the extra thing here is the lifetime. So you have one lifetime for the low loss and one for the core loss. So let's do some focusing now. Yeah, so we have low loss, core loss with the K3. Looks really good. Align zero loss peak. I'm going to stop the acquisition and try to focus on the K3. And again, the way you focus is essentially the same as the other detector. Go here, user tune, FX, and try to make it as sharp as possible. It's getting worse. Maybe there's a lot of FY. Probably, yeah, look at this. Very nice, beautiful. Maybe we have to reduce the sensitivity. fixed as well. And you can even tell the software that, yeah, it looks already pretty good. We have already like 0.5 EV energy resolution, which is the best we can get with this config. So it looks already pretty good. And you can do on zero loss peak clock. We can try to go on zero loss peak clock again. Or you can stop and perhaps try to, or you can even focus here. It really depends. You can do here and maybe try to focus a little bit better. Let's do a little bit S6. It's getting worse. FY again. It's getting worse. Something like that, and FY. Okay, 3 pixel, that's the best we can do. Okay. Now let's go to, yeah, now we're ready to go. So let me reduce this one here. And now we're good to go. Same as before, exactly the same as before. So we're doing DOE also with the K3. Yeah, so we've done everything. Right click on the eye loss. Let's check this data. And let's see that, oh, look at this. So we already gained much better energy resolution with the K3 compared to the other detector. Everything is, so let me move, okay. Let me move this one, let me call it K3. And I'm gonna move it to the watch, sorry, I'm gonna move it, right click, duplicate to workspace 20, okay? So now we have the K3 here. And we have the regular detector here. So let's take a spectrum right there, where we think is right there. So there's about the same place. So this is what you're getting with the regular detector here, and this is what you're getting with the K3. So you're already getting better energy resolution. You can see the peak here. You can see the chromium nicely there. Actually, you can even see the chromium is a split peak. And you know, we have less pixel in the K3. Let's sum more pixels, so we have pretty much the same. Sorry. And you can even go like this and basically sum the same frame. Oh, sorry, that's oh yeah. So about the same area. So you see the improvement. What happens if we go to here on the titanium nitride? See roughly on the titanium nitride. This is a regular detector. So this is the K3, and this is the regular detector. You see the quality is a lot higher. You know, you can actually split you know, the pre-peak of nitrogen more efficiently. Let me show you something very nice, very interesting that we have developed with the with this software. Let's look at the K3 here. So I'm normalizing. So you see the red is, the green is the K3 and the red is the other one. So you probably need the better energy resolution, but you see already the advantage of the energy resolution with the K3. Okay, if you want to explain the last thing, and then I'll show you one more example with EELS, and then we switch to 4D STEM. Okay, let's go back to dispersion 0.9. So I want to show you something really, really cool with the K3. Let's go back to single range. Let's make sure that everything is nicely focused here. Yeah, I'm not going to do anything. I'm just going to make sure it's zero loss. This is, again, the K3. Let's go down in magnification. Okay. We want to map the whole device. I mean, the whole stack from like top to bottom. Something like that. And we want to use that shortest exposure time. Okay. Say that we want to do 1 angstrom. So we'll take 2 minutes. Let's see how it is. We want to do live mapping as well. Okay, so we're going to do the same acquisition over a very large area. Let's make sure to go back to 400 here. Actually, let's do two. Let's do. Let's do 2 angstrom, and then let's sum a couple of frames, maybe 3 frames, 4 or 5 frames. Okay. And then we'll do the drift correction like we did before. And we want to do every frame. Let's put it there. Like this. Okay. Let's make sure that the electrostatic shutter is fully open. Very good. And now we're good to start. So we're going to map the whole area. It's an impossible experiment with a regular detector. We've seen that before. But now this is very much possible with the K3. Almost done, 25 seconds. And then this is possible only with the K3, just because the K3 has much less noise and it can run very, very fast. So we've seen before that you're not able to map the strontium with a regular detector with a very short exposure time because you're dominated by instrumental noise. So this is done. So the software is actually blanking the beam. That's very good. And now it's recomputing all the maps. So this is a massive data set. But we're getting very, very good maps. Look at these. We can put everything together now. So you can put ruthenium, titanium, silicon, nitrogen. Yeah, let's put these ones here, and carbon. You have all the elements here. Looks really good. Actually, I would eliminate the carbon, and I would probably put oxygen, maybe red. Yeah, so you see like very nice quality. And you can go look at the spectra here. We can extract some. It's beautiful titanium. Look at this. The titanium looks really nice. You can even tell, even with the dispersion 0.9, you can tell there is a titanium 4+. You can see the difference in fine structure. We couldn't tell that with the other detector. And you could see already the ruthenium very nicely there. Now, obviously, if you sum more frames, it will get better and better. So you can see there. It's because it was rotated. Okay. Okay. So now let's do the 4D stem. Okay. So let's switch to FTEM. So now we convert our EELS spectrum to an image. So let's look again. We have the lifetime, which control the electrostatic shutter. So on view. Okay, so you see the beam. This is with the K3. You can go in there. All right. So let's change the aperture. We want to put a smaller aperture. So we can do a little bit of kind of like nano beam diffraction. So getting a smaller convergence angle. So I want to run this detector very fast. Yeah, we're still on zone. And so you basically, if you want to run fast, I could go on to 1.4. So here we can run it faster. You can go even to 1.16. It's going to run even faster. Okay. So now you're looking at the central part of the detector if you want to gain speed. So basically, just change. So now we are running this faster. So you could go to 100%. So basically, you open completely. And right now we are running in linear mode, but this is full beam. You see that the K3 actually has dynamic range to do even an intense beam. So, and you can go in counting mode. So let's switch to counting mode now. Even in counting mode, the detector is able to get a nice diffraction pattern. We can actually move with the projector alignment. We can move this to the center. Looks very good. Let me move to the center. Okay, looks good. Let's focus here. This is the last experiment. Yeah, looks pretty good now. But the interesting thing is, let's go up in magnification a little bit. Let's put the beam here on the silicon. On the silicon. Yeah, this is our diffraction pattern, but we want to put a slit because this K3 is at the end. Okay, so let's put a slit. So we have to center the slit. We use user tune. And on D, we could go. So you see the slit now is entering. So now I'm centering the slit. Yeah, so let's actually, let me make sure to have the slit perfectly centered. Again, oh, actually it was, oh, so you see down the slit. Okay, so now the slit is centered. Sorry, it wasn't centered before. So this is, let's take a diffraction pattern. So maybe 2 seconds diffraction pattern. This is with the slit in. And now let's take another one without the slit. Oh, here, sorry. So this is slit in and slit out. You see the contrast is higher. You see these features are more defined with the slit in. And we can look at say this and look at this one too. Okay, so you see a little bit of higher contrast with the slit in. You can explain that, and then I will do some for this stem. So the slit is in now. Okay, so I'm taking one like this. So basically, you just set it up the same way as before. Just go on seabed, and now you're good to go. So okay. Okay, so we took the data really fast, and now you can look at the diffraction pattern moving across the interface. Some changes, you go to here. And when you do like when you scan the central spot move, so you could do the same thing we do. We want to correct this position, so you draw like a box, go to SI and say align SI by peak. So the software is going to measure the center, and it will make sure to correct that. This is already like a big stack, but we've done a pretty fast energy filter for this stem. You see the quality, and this is done in counting mode. Any questions from the audience? I think this was the last experiment. Yeah, the software is going to calculate, just like when you do like the EELS, the correction of the zero loss peak. It's the same procedure is applied to the diffraction. Obviously, in the case of diffraction, an image is much bigger than a spectrum, so it requires a little bit more computing power. But this is now corrected. So you see, very nice diffraction pattern. And you see that the K3 can be used for diffraction, and this is done in counting mode. And you can see look how much is changing inside. And you have enough quality to tell that. Let's see what's happening when you go across this interface. You can study that, and you can even change the convergence angle and see what happens. Everything is fully corrected now. You can see how these the features inside change as we move the beam. I think with this, it's probably all for this workshop. Thanks a lot for attending this workshop. Let us know if you have any questions.